Hey, everybody. Hello. All right. Let's get my drum beat down there. Who needs a drum beat? E to the 2 pi. What's happening? E to the 2 pi. Man. 2i pi. I always forget the I, you know? I feel like the e to the 2i pi is when I kind of stop paying attention. I'm not going to lie. I mean, I've got a degree in math that's sitting around here somewhere. But, yeah, you couldn't pay me to pay attention to imaginary numbers. Is that weird? I don't know. What's up? What is happening? Everybody, happy Thursday. Happy Thursday. Let's see. T-Stove, sound off in the chat. Are you here? Do I see a T-Stove in the house? I'm just checking, because T-Stove put some questions in the, what's up, T-Stove? T-Stove put some questions in the Everyone Loves Math hotline. So, T-Stove, I'm going to just give my quick sales pitch, and then we're going to actually get right into some math tonight. And E, man, if I say man as the collective man/woman, human, E, if you have anything to add, we're talking about exponential growth and decay. So Stove is in college algebra and is a pretty good student. Yeah, we got a test on exponential growth and decay coming up on Sunday, so we're going to do a couple practice problems. So that's what's up. For everybody else, hey, look, right there, that phone number. So that's the Everyone Loves Math hotline. It's also known as my Google Voice phone number. If you got a math question, anything up through like Calc 1, put it in the Everyone Loves Math hotline or put it in the chat. So I've got Twitch chat up here and Facebook chat. I'm trying to share the screen, but it's a little tough tonight. Just a little bit. I probably can move my Facebook chat up here, which is what I should do. Let's move that. All right. This is good television. So yeah, I do your math questions. So if you got math questions, ask them. Stove asked, I think we got 4. Hey, what's up, Nancy? Yeah, we got like 4 questions to do from Stove. And if they're anything like the first 4 that we did earlier today, they're super fun. Everybody's going to love them. And that's just kind of how things are going to go. That's what's up. Yeah, we'll see. We got some time left over. We'll see what kind of fun we have. Okay. So yeah, and maybe a little bit later, if I remember, we'll look at my website and I'll give everybody the hard sales pitch. All right. So, for right now, we're going to get right into T-Stove's questions. So I thought this one was really weird. We had done, let's see, earlier today, Stove and I did Newton's Law of Cooling. We did some half-life stuff. And now we're just looking at, this is just the law of uninhibited decay, which is not as hard as it sounds. It's actually easier than those other problems, I think. All right, so let's check it out. Under certain water conditions, the free chlorine, the free chlorine in a swimming pool decomposes according to the law of uninhibited decay. So, Stove, so that I would look smart, I went and Googled the law of uninhibited decay because I normally don't use that vocabulary, and this is the formula. So this is the law of uninhibited decay. It's actually the same formula as the law of uninhibited growth. It's this formula, which I would describe as like a basic exponential formula, right? This is just like a basic formula. So we can talk about what each of these things means. So let's talk about that. So like A0, me neither. A0, just like it normally is for these problems, is a starting amount. So we're going to call it the starting amount. See, E, you're going to keep me sane by agreeing with me. All right. Let's see here. The K is just going to be some weird constant. So don't really read into it. K is a constant that makes sense for this problem. T is time and A is amount, right? I'm not even going to put that in there. And E is that mysterious number E, 2.7-ish. E, how many digits of E do you know? There's a question for e to the 2i pi. All right. So that's our formula. The only difference between, there you go. I thought there was another 2 in there, but I think you're right. So the only difference between growth and decay is if K is positive, it's growth, and if K is negative, it's decay. That's it. Okay. So let's see if we can come up with a formula for this, what do you call it, for this thing. Okay, so we got a couple of pieces of information. After shocking a pool, the pool boy Jeff, tested the water and found that the amount of free chlorine to be 2.25, to be 2.5 parts per million. 24 hours later, Jeff tested the water again and found the amount of free chlorine to be 2.3 parts per million. What will the reading after 3 days be? And yada, yada, yada. Okay, so they gave us some information up top. They said when he first shocked the pool, so that would be like after 0 hours. After 0 hours, the chlorine is at 2.5 parts per million. So here's what I'm going to say. I don't know where I'm going to put this stove. I'm going to put it down here. But I'm not going to write in red. All right, what I'm going to say is after 0 hours, this chlorine was 2.5 parts per million. That's a data point. That's a point that we can use for this function. All right, and I know that because it said right when the pool was shocked. Okay, then 24 hours later, the amount of free chlorine is 2.3 parts per million. So I'm going to say 24 hours later, the amount of chlorine was 2.3 parts per million. We can just use those 2 points. And I'm choosing to use hours because that's what they're giving us. I could use 1 instead of 24 to represent 1 day, but if they're talking about hours, I'm going to keep it as hours. Okay? Now, we're going to use these 2 points to be able to come up with our equation. And if you remember, our equation was A equals the A sub 0 e to the kt. Okay? So here's what we know. A0 is the starting amount. The starting amount was actually right there. 2.5 parts per million. Right when the pool was shocked, the concentration or the amount of this chlorine was 2.5 parts per million. So what we know is we know that when we're going to make up this formula, it's going to be A equals 2.5 e to the kt. So we know that's going to be in there. Okay, so at this point, all we need to do is find K, and we're going to use this second point to find K. Because this second point is just a coordinate pair to plug in. We can put 24 in for T and 2.3 in for A, and then we can work and find this mysterious constant. All right, so let's go ahead and do that. I'm ready. So what are we going to do? We're going to do 2.3 equals 2.5 times e to the, let's see, the time is 24. So instead of k times 24, I'm going to put 24k. All right, and Stove, this is your problem. So if there's anything we need to, if we need to pump the brakes, you pump those brakes. All right. E, I can't believe I caught you. I can't believe I caught you on that. All right. Sweet. All right, so Stove, what we need to do now is we got to get K by itself. So if I wanted to tell the story about K, Here's K right there. I see it. It's right there. K is being multiplied by 24. Then it's being exponented, right? There's some exponentiation going on. And then there's a multiply by 2.5. So we're going to undo all of those things. And the first thing we're going to undo is multiplying by 2.5. We're going to divide by 2.5. Boom, baby. That allows those to make 1. And now we're going to slide it down. And Stove, you and I have talked about this before. And I know my my buddies in chat are gonna remind us. Don't put this in your calculator. Don't put this in yet, because you do not want to be rounding right now. As gross as it is, we're gonna get K by itself. But we're never gonna round, because once we start rounding, we'll never get the right answer. All right. So now that we've divided by 2.5. Now we need to get rid of this whole exponentiation thing, this e to the. And as Stove and I have talked extensively, y'all don't even know the conversation Stove and I had. The natural log is invented to be the inverse of e to the. And so we're going to natural log both sides in order to cancel out that e to the. That's what we're going to do. And I'm not putting any of this in my calculator yet. I'm just going to let it mellow, baby. There we go. All right. And because I have a microphone, I feel the need to say, I love that natural log is the French logarithme naturel. You all get that for free. Logarithme naturel. Okay. Let's get serious. We almost have K by itself. K is being multiplied by 24. So to get K by itself, we're going to divide by 24. But I think that looks gross. So instead of dividing by 24, I'm going to multiply by 1/24. We could have divided by 24. That's fine. That's fine. But, you know, I think that looks better. I like that better. All right. So we did all of this work. All of this work. And now we can finally give the equation for this weird chlorine problem. All right. Yeah, remember we were talking about some weird chlorine stuff that's happening. All right. So the amount of chlorine, didn't it start at 2.5? Yeah, it started at 2.5. So we're going to have 2.5 as A0. And then E to the KT. So K is 1/24. Ugh. The natural log of 2.3 over 2.5. So we'll put all that up there times T. That is our formula. Gross. Gross, I say. Now, like, when I look at this formula, I do kind of want to simplify it. Like, there's some stuff in here that we could do some more exponent log stuff and simplify it. But I'm going to just leave it like this. I'm going to let my calculator do the work. All right. So unless somebody forces me to do more work with this, I'm going to leave it here. All right. Let's go back up and remember what in the world we are going to do. So we have done all of this garbage. And now finally we can answer the question. The question says, after 3 days or 72 hours, the amount of free chlorine in the pool will be blank. So they want to know what's going to happen after 72 hours. So after all of this mess, the answer to this problem, we just have to put 72 in for T. So this is just calculator from here on out. All right, we just have to be real careful with how we put it in. And I'm going to put it in too. But we're going to do all this work and just put 72 in for T. Okay, so that's going to be the answer. Stove, I'm going to type this into Desmos because that's my favorite calculator, as everybody knows. And let's all just have a moment of silence. All right, I think we all need a moment of silence just for calculator time. All right, I'm typing this in. I'm typing this into Desmos. Let's see here. E to the 2 pi, E to the 2I, E. I'm just going to call you E. E, are you a Desmos fan? There we go. Yeah, GeoGebra's been around for a while. Like, I remember that back when I first started teaching. I think I just didn't like it back then, and it's probably totally different now. Oof. Oof. Let's get that multiplication happening up there, huh? Ooh, I'm going to have to put it here. Times. Oof, oof, oof. Look at that. I don't know if you guys can see where I'm at here. Let's see if I can shrink this down. If I shrink that down, I can make this bigger. So Stove, let me know if you get the same thing as me coming out of your calculator. That's what I got. Oh, there we go. Look at that. Made that nice and big. All right. I should say for everybody watching, one thing I'm getting a little excited about, I'm starting to think about doing some SAT prep, helping people with SAT prep. Getting excited that now the SAT has Desmos built into it. That's pretty awesome. So some SAT work is coming. Oh, it's coming. All right, so Stove, I'm waiting for you to tell me that you're alive and that you were able to get this in your calculator, because this is a nasty thing to put into a calculator. You did get it. Of course you got it. It's not like I didn't think you had it. All right, so Stove, we ready to go on to the next problem? I think that was everything for this particular question. All right. Hey, Stucky's here. What's up, Stucky? Stucky, Stove is here, and we're doing a little, oh, there is more questions. Let's see. So now we need to say, oh, okay. I'm going to go back to my open board here. Here we go. So now I think there's a part 2, Stove. So the part 2 on this says, where is it? It says, I'll highlight it so you can see I'm reading right here. When the chlorine level reaches 1 part per million, Jeff must shock the pool again. How long can Jeff go before he must shock the pool again? So we want to know when this thing, where was that function we wrote? So this function that we had, we want to set this equal to 1 part per million. That's what we want to do. All right, so we can do this. Let's do this graphically. I want to just do this graphically because they were having you do this graphically elsewhere in the assignment. So here's what we're going to do. We're going to do it graphically so that we don't have to work that hard. Okay? So what are we going to change? Let's see. All I have to change to be able to graph this thing is to go up in here, and instead of 72 hours that we put in, I'm just going to put X hours. If I put in X hours, that should, let me reposition my, reposition Desmos here, but that should get us where we need to go. Let's see here. Give me a sec for some rejuggling. I got to juggle. Oh, Desmos. I love you, but please work with me here. Okay, there you go. Uh-huh. We're almost there. Talk amongst yourselves. Okay, so here we go. Here's this weird thing, right? So let's see. Let's remind ourselves. So we're starting here. I'm going to zoom out so we can see this thing. This thing looks flat to us, but it's not. It's just, this is a really like almost flat exponential. I'm pretty sure that if we keep zooming out, we'll see that it really is exponential. It just doesn't look exponential around here, okay? So y'all keep that in mind. So what we want to do is we want to see when does this thing equal 1. So I'm going to set the line y equals 1. So right here, the red line, and am I dark? Yeah, I'm in bold. Okay, so the red line represents the concentration of the swimming pool, right? Remember, it starts out at 2.5 parts per million, and then it after that, it starts to decrease. Okay, I was going to show you. There you go. It starts to decrease. Okay, then the blue line represents just 1 part per million. So what we want to know, Stove, is we want to know where do these two lines intersect. Because wherever these two lines intersect, that's when Geoff has to, go into pool boy motion and do his thing. So let's see. Let's look for an intersection. Is there an intersection somewhere around here? Oh, I got to look closer. All right, where are y'all intersecting? Y'all still getting closer? Y'all still getting closer. You see this? All right, we got to look here. How close are we? Oh, that's the 1. And then the red line, here's the red line. We're just a little above it. See how I'm at 1.112. All right, so we got to keep going. Somewhere it's going to show us the intersection. Let's see. Oh, was it like back here? Oh, there it is. Check that out. Right there. All right, I knew Desmos would find it for us. Desmos knows that we're often looking for an intersection, so I was kind of clicking around where I thought it might be, and look at that, I found it. Now, Stove, in your graphing calculator, there's a way to find an intersection that is more direct, and we can talk about that later, okay? So here's what this says. 263.7 hours, right? That's how long it takes before the concentration in the swimming pool gets down to 1 part per million. 263.7 hours. And so what I want to do is I want to look at the problem again. And let's see. So it says, how long can Jeff go? So what you want to say is you want to say 263.739 hours. Now, if they want you to convert that to days or whatever, you can divide by 24. But that's how many hours it's going to take before the concentration of the swimming pool gets all the way down to 1 part per million. Okie dokes. All right, I'm going to take a breath. Stove, you tell me how you're doing. That was a lot, Stove. Whew. And for the first answer, it would be 1.94. So let's look here. So, I think we did do that, right? Yeah, 1.94 would be the parts per million after 72 hours, right? When we put 72 in for T, then the output was 1.94. Yep, you're absolutely right. All right. Man, oh man. Don't we love exponential growth and decay? so that was one problem that took 20 minutes. Yikes. It also it looks like freed us up from some pesky extra viewers that we had. So, you know, we took care of those extra viewers. I don't know why people don't want to hang around for the exponential growth and decay, but, you know, their loss. It's our party. Okay, so we got the next problem. I'm moving to the next problem. I'm excited. All right, Stove, you ready? You ready for this next problem? All right, we got some more decomposition happening. All right, ready. Okay, so I'm going to read the problem, then we're going to take care of it. All right, here we go. Still got to figure out the height of my microphone because I can't hide the moneymaker up here. Okay, reacting with water in an acidic solution at a particular temperature, compound A decomposes into compounds B and C according to the law of uninhibited decay. So that sentence made me weep, except for the part where it said the law of uninhibited decay, because that tells us what the formula is going to be. I don't think much of the rest of that sentence is going to be important. We'll see. I'm not feeling like it is, but I know that if they're talking about decay, we're going to use the same formula as we did for the last problem. And we should expect that K is going to be negative because we're talking about decay. Okay, so let's see. Next sentence. An initial amount of 0.5. Okay, this is Stove. It's good that you're in chemistry. Capital M. That's moles. Have you gotten to moles yet in chemistry? I don't know if the Stove, you know what a mole is, right? Yeah. So that's what, look at this. Aren't you glad there's so much chemistry in your college algebra homework? What a gift. That's a gift. Okay. But here's the good thing. It says that 0.5 moles was the initial amount. So what that tells me is that A sub 0 is going to be 0.50. So we're already building our formula here, right? All right. So then it's going to give me another data point, remember, just like the last problem, so that I can find K. So it says, I'm going to go back up here, an initial amount of 0.5 moles decomposes to 0.45 moles in 30 minutes. Okay, so what I'm going to say here is, let's see, let's move this. Oh, I'm going to just get it down here. So I'm going to say 30 minutes. We're going to end up with, let me go back here, 0.45 moles. So that point has got to be on our function. And if that point is on our function, then we can plug it 30 in for T and 0.45 in for A, and then we'll be able to find K, that weird constant, right? And don't expect to like have an aha moment with K. It's just some weird, funky constant. All right, so what are we going to write? We're going to write, sorry that you can't see above there, but I can only write so small. So we're going to do 0.45 equals, let's see, what was our starting amount? 0.5 e to the 30K. All right, so all we did for that is we put 30 in for T and 0.45 in for the amount. That's what we did there. So we've got some steps to work to solve to get K by itself, but those steps are going to look familiar because we've already done them in other problems. So what I mean by that is that the very first step we're going to do is divide by 0.5 on both sides. All righty. That's a 5-0. Man, look at that. Woo, boy. That's an O. Okay. So we get this fraction C equals e to the 30k. All right, so now we've got e to the, we want to undo that e to the, so now's about the time to do the natural log of both sides. So we're going to do the natural log of the left side, do the natural log of the right side. And I'm just going to copy the left side. Nothing to do there yet. Don't want to put it in my calculator. I don't care. Calculator can do the math later. And now that we've done the natural log of both sides, I'm going to multiply both sides by 1 over 30, because that's going to get k by itself. We also could have divided by 30, but I just think this looks cleaner. And I'm the one holding the marker. So, you know, when you're holding the marker, you can divide by 30. That's a promise. That's a promise from me to you. All right, so now we have k. So now we can go and write this function finally. So we can say, after all this work, a of t is equal to, we had 0.50 e to the 1/30th times the natural log of garbage times t. There is our formula. All right. Okay. So now the question is it time to graph this thing or what? So now that we have this formula, I'm going to be honest with you. I forgot what I was doing because I was just in formula land, right? So what we're going to do is we're going to scroll back up and be like, all right, I got this stupid formula. What did you want me to do? So now I'm going to go back up here. So the question says, how much of compound A will remain after 2 hours? That's the first question. It looks like there's 2 questions in here. So one says, how much of compound A will remain after 2 hours? So let's see. We have our formula. All we have to do is put 2 hours in, but there's a catch. There's just one catch. For T, we've been using minutes up until now. Remember that? Remember when we said after 30 minutes, the concentration was 0.45? So we've been using minutes. And all of a sudden, they ask us something about 2 hours. So here's what we have to do. We have to say, all right, you're not going to fool me. We can't put 2 in for T because 2 would represent 2 minutes. We got to put 120 in for T because 120 represents 120 minutes, also known as 2 hours. Ooh, boy. You love it. All right. So T-stove, it's now time to let your calculator do the work. All right. So I don't know why I've been saying moment of silence. Moment of silence for some calculator work. Here we go. I wish I could just, I could put on some music. I should remind myself to do like, record like a copyright-free version of the Jeopardy theme or something, That would be cool. My favorite thing about saying silence is that I immediately violate my own rule. Like, immediately. T-stove probably has me on mute right now. That's what I think. All right, I think I got an answer. I think I got one. I'm going to project it, Stove, so you can check your work, okay? That's what I got. You tell me how we're looking. T-Stove, tell me how we're looking. Tell me how we're looking, T-Stove. You got it. Nice. All right. So that number, 0.32805, so that is measured in moles, right? So that's 0. Let's see, they want it rounded to the nearest hundredth. So I would write 0.33 moles, right? That would round up to 0.33 moles. Okay. Good times. There's one more question in here. It says, how long will it take until 0.1 moles of compound A remains? So last time I showed you how to do this graphically. This time I can show you how to do it algebraically so that you know how to do it both ways, okay? So let's go down here. This time, instead of giving us, remember last time? Hey, remember this part? I remember. Oh, you don't remember because you can't see it. Look at that. So I remember when we did this because it was like a minute ago, and I have a great memory as long as it's like a minute. So they had given us, what did they give us? 2 hours to put in for T. So we put, 120 minutes in for T, and we found A. Well, in the second part of this problem, they give us A, and they ask us to find T. So they say A is 0.1. So I'm going to put that in instead of A. I'm going to write 0.1 equals the rest of this formula, 0.50 e to the, and this time the variable is going to be T. What's that? 4,5, right? Over 0.50, and then times T. All right, and that's a 5, 0. All right, so do you see the difference between part A, I guess if you want to call it part A? So the difference between part A and part B is that in the first part, they gave us a number to plug in for T, and in the second part, they gave us a number to plug in for A. So we plugged in the number for A. Now we just need to, if we're going to do this algebraically, we need to do the algebraic work to get T by itself. All right, so we've done this before. We're just, we're going to do it again. So let's see here. If I'm going to get T by itself, the first thing I have to do is divide by that 0.5. All right. And then I could keep this decimal 0.10 divided by 0.5, but I know that that's really the same as 1/5. And so I'm going to leave that as 1/5 because I think that looks easier. Okay. Normally I wouldn't simplify it, but in this case, that looks simpler to me. Okay, so now what do we have? We have e to the garbage. All right, so we're going to fill out all this. All right, so we're looking at that. You love it. Okay, so we're still trying to get T by itself. T is trapped up in that exponent. So just like you and I have talked about before, if we want to free T from that exponent, we need to undo e to the, and we undo e to the, let me get another color, by taking the log of both sides. And because the base is e, we're going to take the natural log, the logarithme naturel. Logarithme naturel. As much as that I whispered that in the ear of girls in college, it never got me anywhere. I don't know why. I don't know why. All right, so we're going to leave the left side natural log of 1/5. The right side, we did the natural log of e to the, and so those undo each other. So we're just going to have 1 over 30 times the natural log of 0.45 over 0.5. All of that times t. Okay. So, going to be honest with you. I'm sick of doing this problem. Sick of it. You're sick of it. We're both sick of doing this problem. This problem's too long. So we're going to get t by itself in the laziest way possible, okay? This thing, 1/30th the natural log of 0.45 over 0.50. This thing is disgusting. First, we're going to let our calculator handle it, but this whole thing is being multiplied by t. So if I want to get t by itself, I'm going to divide both sides by that whole monstrosity. 1 over 30 times the natural log of disgusting. All right, we're just going to divide that. And at this stage of the game, I'm almost like, I don't care how ugly this looks. It's just going to be a decimal anyway. Gross. We want all of that to cancel. Ew, gross. And so the answer to this problem, for how much time it takes, we're going to write, then we have to do all of this into our calculator. And yeah, we could have cleaned this up. Like, there's things we could do to make this prettier. But, like, I know where stove is. I know where I am. Let's just make the calculator do the work. That looks disgusting. Desmos is a robot. Make Desmos do it. Okay? So, let's go back to Desmos. I'm going to put it in. All right, or actually, stove might need to see that. So let me leave it up. I'm going to put it into Desmos once I find my mouse. There it is. And then stove, you and I can check answers. Yeah, this was gross. I'm so mad at you for giving me these problems. All right, I'm going to switch it over here. If you don't want to see the answer, don't look up. Oh, I did. I'm going to make that look like I said I would. There we go. Yeah, stove, we're matching. That's a second got it from you, isn't it? Look at you. All right. So after all of that work, whatever this 0.1 concentration is, right? Whatever that is, it's going to happen. Twinsies! It's going to happen after 458 point, whatever that is, right? So we're going to say, let me go back to my open board here. So we're going to say this happens after 458.27 if we're rounding to the nearest hundredth. I think it's a hundredth. And that's in hours. Remember that we're using hours. Wait, we said minutes, didn't we? This was a minutes thing. So that's 458.27 minutes. All right, yeah, if it's round to the nearest tenth, then that's what we just did. Bleh. Bleh. Hey, we're getting better, stove. That one only took us 19 minutes. Don't you love exponential decay? Hopefully the next problem gives us a little bit of relief. It sure would be nice to get like a true or false question or a fill in the blank or something up in here. You know what I'm saying? Stucky knows what I'm saying. If you're rounding to the nearest hundredth, you would have to round up to 458.27. right? Because if you look at the decimal in Desmos, Stove, it's 458.265. So that 6 would round up to a 7, right? Because that 5 is in the thousands place. Oh, wait, it said nearest tenth? So if we're rounding to the nearest tenth, then we only have to look at the 2 and the 6. This would be 458.3 if we're rounding to the nearest tenth. Right, because the tenths place is the one right after the decimal. I'm glad that you're paying attention to it, because that is the worst way to get this problem wrong. Yeah. That's the guaranteed way that I would get this problem wrong, is I would do all this and then round it to the hundredths place. But that is life. That is the life that we live. All right. Hey, I think we're halfway there, Stove, with all of your questions. All right, so what do we got? Do we got another decay? It looks like we got a little half-life decay kind of issue. All right, so let's go down here. After the release of radioactive material into the atmosphere from a nuclear power plant in a country in 1986. Gee, I wonder what country that was. The hay in that country was contaminated by a radioactive isotope. The half-life was 7 days. If it is safe to feed hay to cows when 14% of the radioactive isotope remains, how long did the farmers need to wait to use this hay? So Stove, let's talk here. So once again, we need to come up with the formula for this. Now, you and I have done a half-life problem. We've done a problem where we've made the equation so that the base was 1/2 when it was half-life. But one thing that I didn't mention at the time is we could also use this formula for the uninhibited decay. We could also use that formula if we wanted to. Either of those formulas work, okay? So I think maybe we'll use the one that you and I developed together, and feels like cheating, but we did this earlier today. It's like a cooking show when you're like, oh, this lasagna is coming out of the oven. So what did we say? We said it was the starting amount times 1/2 to the t divided by half-life. So that was the formula for half-life that we had come up with earlier today. And so what I think we should do is I think we should use this formula. Nancy. So, yeah, exponential growth and decay. Nancy, tonight is a rough night, man. Stove is not messing around. If anybody here thought Stove was messing around, she is not messing around. All right. So, let's see. Dude, it is rough, man. It's rough. But you know what? Tomorrow's Friday. And we're spending time together. I think that's really what's important here, is the time together. All right. So Stove and I already worked out this formula for half-life. So I kind of want to use this. Except, let's see. The half-life is 7 days. So what I'm going to do is I'm going to put 7 as the denominator up here. Okay. And then it doesn't tell us how much we started with. It doesn't tell us the initial amount, but it asks us how much time do the farmers need to wait for the amount to be 14% of the original amount. So we've actually, Stove, you and I have done a problem like this before as well. What we want is, if the original amount, we don't know, we'll just call it A0 because that's what's in the formula, right? So if A0 is the original amount, then 14% of that would be 0.14 times A0. That's the equation that we need to make. And I'll say it again, we could do that that formula for the uninhibited decay, that formula will also get us a right answer. But so will the half-life formula that we came up with earlier today. All right, so with this formula, once again, these problems where they don't tell you the starting amount, if you set it up like this, what happens like every time is the A0, we can divide both sides by A0 and they'll disappear. So check that out once again. If we divide both sides by A0, then the A0s cancel out on the left and the A0s cancel out on the right. And if we do that, we will have, let's see, 0.14 equals 1/2 to the t over 7. All right. All right. And we're pretty close to being done with this one. So what we have to realize is that t is being divided by 7, and then it's trapped in the exponent of the 1/2. So this is one where we have to undo the exponent. We're going to do the log of both sides. And I'm just going to do the log base 10 of both sides. I'm going to do that because I know we're going to have to stick this into our calculator. And log base 10 is on our calculator. And I know that whenever I've asked Stove which base she wants to use, she says 10. So we use 10. We could do base E. But you don't know Stove like I do. So we do base 10. All right, so what's going to happen over here on the right? Well, we did that so that we can use that bring down the exponent rule. So we have t over 7 times the log of 1/2. All right. So at this stage, we're close to having t by itself. What's happening to t? T is being divided by 7. I see it right there, right? T is being divided by 7, but also multiplied by the log of 1/2. And because I'm a cool kid, I'm going to undo both of those right now. I'm going to multiply both sides by 7, because that's going to undo the divide by 7. And then I'm going to divide by the log of 1/2. Because the 7s will cancel, the log of 1/2 will cancel, and we're going to be left with just plain old t equals disgusting. There we go. All right. So this will be the time that it requires in order for 14% of that radioactive stuff to be in the hay. So once again, we're going to let our calculator or Desmos do this work for us, because last time I checked, it was 9:56 p.m. and I'm going to let the calculator do as much work as possible for me. You know what I'm saying? All right, so I'm going to go up into Desmos and put this thing in. Stove, you put this in your calculator, and let's check and see how we're doing, okay? Here we go. All right. I think I got an answer for us. I'll put it up, Stove, and then you don't look. You don't look. I'll put it up. There we go. Hey. All right. And we'll talk about what the heck that is in a minute. Ooh, you're fast, Stove. Look at you. Look at you. You and I are twinsies yet again. Twinsies yet again. Look at us. All right. So what this means, what are we doing? So we are, let's see, time is being measured in days. Okay, so let's remember that. And they ask us use round to 1 decimal place. So if we're going to round to decimal place, we would say 19.9 days. All right, 19.9 days. Yeah. Aren't these fun? These are fun. These problems. This is just like a meal. Isn't this like a meal? These problems are a meal. That's what I'm saying. All right. The next one looks long. Okay. All right. The next one looks long. That's what T Stove says. I'm going to flip over to it. We're going to read it. Yeah, they sure do. They sure do have F parts, don't they? Okay, here we go. Stove. Dive in. For those of you that are just joining, Stove, let me give my quick commercial. I'm going to give my quick commercial. For those of y'all just joining, yo, what's up? I'm Joey. Welcome to Everyone Loves Math Live. I do this show Monday through Thursday, starting at 9 o'clock, ending whenever. And we do math. Anything up through Calc 1. If you got a question, you ask it in the chat, Facebook chat. You can ask it in Twitch chat, or you could ask it on the Everyone Loves Math hotline. The hotline is the phone number that's going to scroll at the bottom of the screen. That hotline's my Google Voice number. When we don't have any questions, we play some video games. But right now, we're talking about exponential growth, exponential decay, and it's been a good time. We've been going all night strong. All right, that having been said, let's do potentially our last exponential problem for the night. Now, here's one thing, Stove. Let's talk about one thing that makes us... There should be one thing that makes you excited about this problem. So here's what I want you to do. Tell me the one thing that makes you excited about this problem. Besides, it's the last one. You can't just say it's the last one. And if somebody in chat wants to help out Stove, I got excited just now. I love a chat delay because that definitely doesn't add to awkward silence, huh? Stove, I'm not going to go until you tell me why you're excited. Yeah, we have a formula for that. Not only do we have a formula for that, we don't even need a formula for that because they straight up gave us a function. Look at that. So this is hopefully what you're saying is what I'm saying is look at this. This is what makes me excited right about here. That makes me a very excited young man. Because finally they gave us the function, so we don't have to do the work to find the function. Okay, so hopefully it's not just there for decoration. Let's read the problem and dig in. So the size p of a certain insect population obeys this function. Okay, so t is days, and p would be the population of whatever insect this is. So the first thing it says is determine the number of insects at 0 days. So looking at this formula, there's a couple of ways to do that. We could put 0 in for t, right? Like we could totally do that, but we don't even need to do that. And the reason is because the coefficient here, 500, that is the starting number. But you know what? Just for kicks, let's put 0 in for t. I'm going to do it just so that we have some good notes. How about that? So the number of insects at 0 days is going to be a of 0 equals 500 times e to the 0.03 times 0. So if they ask us about 0 days, we're going to put 0 in for t. When we do that, and yeah, I did write in red, and I know I hate red. So when we do that, this is going to be 500 times e to the 0 because 0.03 times 0 is 0. Now listen, anything to the 0 is 1. So this is just 500 times 1. So what that means is is at 0 days, the population of insects was 500. There were 500 of these little bastards. Pardon my language. Pardon my language. Is it 10 o'clock yet? It's 10:02. Kids should be in sleep. Kids should be asleep. But also, pardon my language. All right. So 0 days, 500 insects. All right. So now that's part A. Don't worry, we've got part B coming. So what is the growth rate of the insect population? What is the growth rate? All right. So I think to do the growth rate, let's see, I haven't done this in a minute. Is that just e to the 0.03? I think the growth rate is just that part. Can y'all check me in chat? Because what happens if we put e to the 0.03 into the calculator? I think that tells us about the growth rate. True that, Nancy. Okay, so let's see. Remembering that the variable here, the t, is measured in days. If I put e to the 0.03 into my calculator, this gives me 1.0304. So I'm wondering if the growth rate, if we write this as a percentage, this is 103.04%. So I'm pretty sure the growth rate is 3.04%. And sorry for writing that kind of weird. I apologize for that. I'm just doing some brainstorming here. But I think that's the process to find the growth rate as a percentage. Is we just do the base part. All right, so up next, it asks us to graph this function. It does not like that answer. Well, I'm sorry. What is the growth rate of the insect population? So the growth rate would be 3%. Okay, you could try 1.0304. You could write the decimal here as the growth rate, that 1.0304. See if it accepts that. You could also put e to the 0.03 in as the growth rate. I'm not sure what it's going to accept. But it's some form of that as the growth rate. All right, and while you wrestle with that, I'm going to graph this because it asks us to graph it. So I'm going to head to Desmos and do a little graphing. There we go. It said the correct answer was 3. So I guess they wanted the percentage, Stove. They probably wanted the percentage rounded to the nearest whole number. Yeah, that's dumb. That's dumb. Whatever they just did was dumb. Okay. So Stove, while you were wrestling with that, I went ahead and graphed this thing in Desmos. So here is what this thing looks like. So it's definitely, I know it's dumb, I'm sorry. So it's definitely exponential. So we're looking for an exponential graph where the y-intercept is at 0,500. So I'm sure for part C, they probably ask you to like match this graph to one of them. You just want to find a graph that looks like this and has a y-intercept at 500. And I bet you There's only one graph that does that, right? I bet you. All right. So next up, I'm especially since it's after 10, I want to use Desmos to answer these next couple. So question D, it says, what was the population after 10 days? So I'm going to show you a little Desmos trick. I'm going to change this equation from y equals to f of x equals. Because if I want the population after 10 days, I can just say, what's f of 10? And that tells Desmos to put 10 in for x. All right, there's a little trick. I like that trick. Wanted to share that with you. So what that means is for these little insects, after 10 days, there would be, depending on how you round, there would be almost 675 of them. All right, however you round. All right, I'm checking your hotline. Let's see. Ooh. Ooh. Didn't like that question at all. Choose the correct graph. Oh my goodness. Yeah, they gave you a nasty one, huh? All right. So, man, yeah, this is gross, Stove. This is really gross. I'm gonna project this so that we can see it and talk about it, okay? So I think I'm sending it. There we go. It's coming in through the hotline. Via airdrop. We're making all kinds of moves in here. Here we go. Let's see here. Let's add a page. There we go. And then I'm going to go and find this. I can never find my mouse. Okay, let's see here. Let's go over here. Downloads. We're going to grab that. Yeah, that thing. We're going to grab that. I didn't want to open it. Let's see. Yeah, I don't want to open you. I want to drag you over here. There we go. Okay, so let's see. Go back to open board. All right, so this is what Stove is dealing with, right? We're trying to match that graph. So let's look at this ugly multiple choice because they didn't do us any favors, okay? All right, so let's look at this thing. So what's happening? So first of all, the x, remember what all this stuff means, right? The x's go from 0 to 10 and count by ones. The y's go from 0 to 1,000 and count by hundreds. Okay? So here's one thing I can totally do. Check this out. I'm going to go back to Desmos, right? And I know my answer to everything is Desmos, but I'm going to go and hit the little grapher boy, and I'm going to make it do the same x and y. So I'm going to say, hey, on the x-axis, why don't we go from 0 to 10, 0 to 10, and we're going to count by ones. And on the y-axis, we're going to go from 0 to 1,000, and we're going to count by 100s. So what I did there is I set my the x-axis and the y-axis on the graph for Desmos the same as they set it on the homework. So now that I've set it like that, now I think it's going to be more obvious which one this equals. This is going to be B, because if you compare this to what's on here, so A like decreases, right? Look at A. A decreases. C looks like it stays the same, and D starts at 0. But B is the one I'm kind of feeling, right? B starts at 500, which it should, and then goes up a little from there. All right, so in this particular case, the graph that matches, I'll go back here again, the graph that matches is B, okay? That's a fun boy right there. That one's fun. I love it. Love it. All right, so now let me go back here. Let's go back here. And now, Stove, now we can answer part D. And part D, going back to where we were at, part D is right there on the second line of the graph. So I made this function f of x, and I asked Desmos, what is f of 10? Because that'll tell me how many insects after 10 days, f of 10. Okay, and the population is almost 675 insects. Okay. All right, just checking that my stream is up. Boom. Okie dokie. Are you ready to keep moving? You tell me when. Because we're going to do the rest of these. Ready. Okay, we're going to do the rest of these problems with the graph, okay? So, because it might feel like cheating to do this with a graph, and I hope it does. I hope it feels like cheating to do this with Desmos, because you should totally do this with Desmos. It's not, if they let you use a graphing calculator, this is not cheating. Okay, so next up, it says, when will the insect population reach 750? So what I'm going to do is I'm going to get rid of that f of 10. That was for the last one. I'm going to give an equation y equals 750. And now we can look and see. I'm going to give this a different color because I don't like it. I don't like blue and purple on this. You know what I mean? Like, let's make it red. Okay, so the red line represents 750 insects, and the blue line models the insect population. So I just want to know, when do these intersect? Whenever these intersect, that'll tell us when there were 750 insects. And look at that point right there. All right, remember that T is being measured in days. So what we would say is that on the 13th day, right? On the 13th day, after 13.516 days, there will be 750 insects. Alrighty. And now I'll go back here to where we were. All right, and now let's look at our last problem. So the last problem, part F, it says, when will the insect population double? And so this is another place where we can overthink it, but I would say don't overthink it, okay? Remember, we started with 500 insects. Yeah, if it's 13.6, if it's round to the nearest 10th stove, then yeah. Yeah, just follow the directions for rounding. So if we're talking about when will the insect population double? Well, we started with 500 insects. So if we want to know when will the population double, then we want to know how long will it take for there to be 1,000 insects, because 1,000 insects is double 500. So all we need to do is go back to Desmos, and instead of looking for where this function equals 750, let's look and see where this function equals 1,000. And I'm doing 1,000, remember, because 1,000 represents double what it started with, double that 500. All right, well, I can't see this function. Why? Because it's up there, right? 1,000 is up there. So let's see where our insect function hits 1,000 insects. Right there. Look at that number. So after 23.105 days, there will be 1,000 insects. Gross. So, Stove, one thing that we may need to do, and you let me know, and I can do it during one of the shows next week. We can talk about how to use your calculator, because I know you're not allowed to use Desmos on a test, which is messed up. But if we need to have a little little calculator day next week, we can do a little calculator day, because you can totally do this on a graphing calculator. Yeah, absolutely. All right. Dude, that was a lot of math. How's everybody doing? Everybody doing all right with the math? Let's just check in with everybody. It's Thursday night. Everything is great. Today was an awesome day. Yeah, Stove is going to cry herself to sleep. So I think we can all wish Stove a good night. Believe it or not, Stove, if you look at the clock, you and I have spent 2.5 hours talking about exponential growth and decay today. Yeah, Nancy, too much math? Yeah, see, Stucky's going strong. Stucky's just getting warmed up. But yeah, Stucky, Stove and I did like almost an hour and a half before we got on. So yeah, it was a big night. But let's all wish Stove a good night. Stucky, you're always so nice. You're always so nice to the people. All right. Good night, Stove. So, there you go. So I should mention, and Stove, you go ahead and log out. So Stove, I have known her, let's see, I think I taught Stove 10 years ago. And Stove is back in college, and kicking butt right now in college algebra. And then Nancy, if I want to feel really old, Nancy, I taught, what did I do? I taught Nancy 15 years ago. Oh, nice. E to the 2I pi. You're a student in his or her analysis class. Word. Look at that. (2009) so 2009, Nancy. Yeah, 15 years ago, right? So yeah, Stucky, let's see. Dude, we talked about this yesterday. So, Stucky, I think it's called Whisper on Twitch. I'm going to whisper you, my contact info. Or actually, Stucky, I'd love to be your pen pal. Do you want to email me? Because, I can put my email in the chat. It's on my website, my business email. Because I would love to start making some evil plans. Get this Twitch math thing, official. So, I am Joey at everyonelovesmath.com. And you are welcome to send me an email, and we'll get chatting. Because I think we can have some fun. I'm already having fun. Well, let's see. It's 10:20. That was a whole lot of math. I'm feeling pretty mathed out, so I think I'm going to call it a night. I think so. I think I'm going to also do some game streaming this weekend. I'm in the mood for a little bit of game streaming. Maybe some Balatro this weekend. I did win a game of Balatro earlier today that no one saw. Yeah, and Stucky, I'm not on Discord, but I keep thinking I need to get on Discord. I think I need to be part of someone's Discord so I can see how cool it is and how to use it. But when I first started this business, I tried to get on everything, on all the social media stuff, and it's pretty overwhelming to do that, especially since I'm on Twitter, and I don't want to be on Twitter. But I have a Twitter account. So yeah, I need to figure out the social stuff. I feel pretty good about Facebook, and I'm building Twitch, and that's about where it's stopping. So yeah. Yeah, dude. Yeah. So, all right. So anywho, let's wrap this up for the night. Thanks everybody for joining. Tonight was fun, even though it was laborious and mathematical. Join me every, what are we doing? We're doing Monday through Thursday at 9 o'clock until whenever. We do some math. We have some great times. If you want private tutoring, I do offer private tutoring through everyonelovesmath.com. I've got hourly rates and a monthly subscription up there. It's good times. And I'm here to be your math cheerleader. So if you need help with math, let me know. Nancy for Bellatro, I am not sure. I will. I probably won't schedule it tomorrow, but I just need to see. I need to see what the wifey wants to do tomorrow night. So I may end up streaming during the day. Depends on what my day looks like. But if depending on where we are at night, I might do like a 10 o'clock Eastern time stream. All right, we'll see. All right, DM me on. Oh yeah, I will. I'll message you on Facebook when I stream. Or I think if you're following me on Twitch, so I think you also, if I start streaming, I think you get like a random notification. So yeah, I'm still just learning all this stuff, man. That's why I need y'all. Y'all have been awesome. All right. Enough with my long goodbyes. Everybody have an awesome night. If I don't see you, have an awesome weekend. We'll be back at it Monday at 9 o'clock. And until then, y'all keep it classy, keep it mathy, and we'll catch you later. Good night to everybody.